Hello everybody, and welcome to another lecture on computer architecture. So this final video about this series about small components that are essential for computers, I'm going to finish with the coder and the decoder, which are very similar to the circuits I've just shown in the previous video. So let's take a look. Here we have the demultiplexer that I showed you last time, where the data line itself is going to be copied to one of the four output lines, depending on the selector lines S1 and S0. And once again, I just take here an example of it, four output possibilities, and therefore the needing two selector lines, but you can have this maybe 64 of those and then 6 selector lines. The idea is what counts, and I just take simple examples, otherwise the picture becomes too complicated. So now what are we going to do now? We're going to remove D, so it's not data. The data will be always, let's say, always 1, so I will put here data 1, and then it's redundant actually, because 1 and something is the same as that something, as we know from the Huntington postulates from the beginning from our digital systems. 1 and something is actually the same as that something. So if D is always 1, I can remove it actually from the AND gates, and then we get what is called here a decoder. So you can imagine that here all of them have the data line, but the data line is 1, so it is redundant, and we just have only the selector lines. I wanted red, only selected data lines, and once again now one of these combinations will be 1 appearing as 1 1. Only at one AND gate it will appear as 1 1. So once again, or let me now take another example, and let me for instance take 0 1, and you will see here, so here it will appear as 0 1, here this 0 will be inverted, so it's 0 0. This one as 1 is inverted, so it's 1 1, and here both are inverted, so it is 1 0. And as you can see, 0 1, 0 and 1 is 0, 0 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0. So only one and only one of these Z lines actually has a 1, and the other ones all have 0. Now, why would this circuit be important? Imagine now that I have here 4 memory chips, or maybe 4 components. It could be maybe the program counter or the instruction register or memory. At least, let's say 4 components that are all connected here to a communication bus. So let me write it here. This is a communication bus, and they are all connected to it. But of course, they cannot all talk at the same time. Actually, only one of them has to do the calculations. But for simplicity's sake, let's assume that we have here 4 memory chips, and only one actually can place its contents on the bus and communicate here. Maybe this here is with the CPU. So how do I do this? Well, this line I can put here to what is called chip select, or CS, chip select. That means it will activate that chip. And in this case, as you see, this one will be deactivated, this one will be deactivated, and this one will be activated. And for instance, this chip select is also used to put the output here, remember, in tri-state. Remember the tri-state about CMOS technology, how to put things in high ohmic state to put it in tri-state, that it will not communicate with the bus and it will not cause a short circuit. But if it is taken off tri-state, then the contents of the memory are placed on the bus. And of course, we call this a talking. And of course, only one of these elements can talk. The rest have to listen or be deactivated. And with this chip select, we can deactivate a chip, activate and deactivate a chip, and one of them can be put into talker mode and place its contents on the communication bus, and then the CPU in that case can be listening, or maybe also can be one of those can be actually connected to the CPU, can also be placed in talker mode, namely when it wants to write to memory. You get the idea. So here you will have control control logic that is then generating these selector lines, and these selector lines will make it so that only one component actually communicates to the bus and the other have to listen or to be doing nothing at all. This is what we call a decoder. And finally, for completeness sake, let's also talk about this encoder. And for the encoder, now I wanted to show you this. Actually, what it wants to do, what it should implement, is to put in a binary code to say which of these 4 input lines is 1. And in case there's more than one, it should say the highest number, that is 1. But at least one of them is 1. This is the condition. One of these lines is 1. And I want to know here in binary code which of these input lines, data lines here is 1. So we get this thing. If this D3 is 1, it doesn't matter the other, because even if one of the other, this is also 1, then D3 is the highest. So it should output 1, 1. So you can see if D3 is 1, it doesn't matter the others. The output should be 1, 1. And if D3 is not 1, if it is 0, then we check if D2 is 1. If D2 is 1, then it should output 2, so that is 1, 0. So then if D2 is 1, then it doesn't matter the others, the output should be 1, 0, which is binary 2. In the cases this one is 0 and this one is 0, then we check if this one is 1, case correct, 1 means binary 0, 1, so it should output 0, 1. As you can see, 0, 1. In case this one is 0 and this one is 0 and this one is 0, then we know D0 must be 0, because I said at least one of them is not 0. So, and you can see then that in that case, if this one is 0, this one is 0 and this one is 0, it doesn't matter. I don't even want to know. My logic doesn't care then, because I know it is 1. Because 0 is not possible. So I have the output 0, 0. And as you can see, the D0 doesn't matter at all. It's don't care. So my logic, as you can see, the implementation, Carnot maps and everything, it will completely bypass D0. And in this way, the line with the 1 is then coded into the binary into the Z1 and Z0 values. And this is called an encoder. So I've talked about an encoder, a decoder, a multiplexer, a demultiplexer, and a level shifter. Shifter, left-right shifter. And these are some basic components that are used in computers. So see you in the next lecture, where we will talk about other things. See you in the next lecture.